Today we're going to be talking about section 5.1 from your textbook. This is a section on eigenvectors and eigenvalues. Before break, we had talked about matrix multiplication as a transformation. So if we multiply a matrix times a vector, that takes that vector and sends it to a different spot. So for instance, if we have our vector u and we multiply by a, maybe it sends it to this other vector over here, a times u. And there's not always an immediate sort of geographical, I guess, or geometric relationship between u and au. But sometimes if we multiply a specific vector times a, what we get is a scalar multiple of that vector. So for instance, maybe a times v gives us this sort of stretching out of v. And that's really interesting because we can see that a times v points in exactly the same direction as v does. We're just stretched out. So that's what we're going to be talking about today. This is called, v in this case is called an eigenvector, and the amount that it's stretched out by is called an eigenvalue. So a scalar lambda is called an eigenvalue of a if we have some vector x where when we multiply a by x, it just stretches x by that amount. So ax equals lambda x. So in this case, lambda would be the eigenvalue, and the x corresponding to it would be the eigenvector, or an eigenvector. So let's take a look at this in action. This is example 1 from section 5.1. So example 1 is saying, here's our matrix A. Are these two different vectors, u and v, are they eigenvectors of A? So again, something is an eigenvector of A if when we multiply it, we get a scalar multiple of our original. So let's start with u and try actually multiplying out a times u. So if we multiply a times u, this would be minus 3 minus 2, so that would give us a negative 5. And minus 1 plus 0 gives us a negative 1. Is minus 5 minus 1 a scalar multiple of negative 1, 1? Well, we'd have to multiply negative 1 by 5 to get negative 5, but if we multiplied 1 by 5, we'd get 5, not negative 1. So this is not a scalar multiple, which means that u is not an eigenvector of A. Let's try out with v now. So if we multiply a times v, then we get 6 minus 2 is 4, and 2 plus 0 is 2. Is this a scalar multiple of our original? Well, if we do 2 times 2, that gives us 4. 1 times 2 gives us 2. So we can factor out a 2 and say this is 2 times our original vector v. So that means that v is an eigenvector of A, and it has a corresponding eigenvalue. So the eigenvalue that's related to this eigenvector is going to be that 2 that we found. So that 2 that we pulled out. And we can see this graphically or geometrically. If we look at this graph here, in blue is our u. And when we multiply by a, we get negative 5, negative 1. So that's going to look something like this. So this would be our au, and you notice that those are not pointing in the same direction. So u is not an eigenvector. If we look at v, however, if we look at a times v, we get 4, 2, which is this. It's pointing in exactly the same direction as v was pointing. So v is an eigenvector. So we just talked about how to figure out if an eigenvector, or if a vector is an eigenvector of A. Another question, a related question we can ask is if we're given a scalar, is that an eigenvalue of A? So, but before we do that, let's do another example. So this is problem 6 from section 5.1. So this is asking, is this vector u an eigenvector of A? So again, we just multiply a times u and see if we get a scalar multiple. So if we multiply this, we get 3 minus 12 plus 7, so that would be negative 2. And then we've got 3 minus 6 plus 7, so that would be 4, and 5 minus 12 plus 5 would be negative 2 again. Okay. Is this a scalar multiple over 1 minus 1, 1? or sorry, 1 minus 2, 1. Well, 1 would have to be multiplied by negative 2 to get to negative 2. So let's try negative 2 as something we pull out. So if we pull out a negative 2, we get 1 minus 2 and 1. Great, that worked. So that means that our u is a scalar multiple when we multiply it by a. So that means that u is an eigenvector of a, and its corresponding eigenvalue is going to be the minus 2 that we pulled out. So if we want to see if a specific vector of u is an eigenvector of a, we just multiply a times u and then see if the answer is a multiple of u. If it is, then u is an eigenvector and the multiple is the eigenvalue. And if it's not, then it's not an eigenvector. Okay, now we're going to see how we figure out if a given scalar is an eigenvalue. So we saw is a given vector an eigenvector. Now let's see is a given scalar an eigenvalue. So let's change colors. If lambda is an eigenvalue of a, then by definition, ax equals lambda x has a non-trivial solution. So I'm going to go ahead and see if we can simplify this into something we can work with a little bit better. So let's start by moving lambda x over to the other side. So we're going to subtract lambda x from both sides. So if that's true, then this should also be true. This should also end up having a non-trivial solution. And all right, so now we're looking at ax equals ax minus lambda x equals 0. What can we do with this? Well, we notice that both of those are multiplied by x, so we can factor an x out. So this, if we factor an x out, this would look like a minus lambda times the identity matrix times x equals 0. And so this should also have a non-trivial solution because we just factored out an x. Why does it end up looking like a minus lambda I? Well, we multiply lambda times I because lambda itself is a scalar, so we wouldn't be able to subtract that scalar from our matrix A. But if we multiply it by the appropriately sized identity matrix, then that would work. I should mention in all of this, A is a square matrix. Okay, so to recap, how do we tell if lambda is an eigenvalue? Well, if we have that setup, that homogeneous system that we just came up with, so a minus lambda I times x equals 0, if this homogeneous system has a non-trivial solution, so in other words, if it has free variables, then lambda is going to be an eigenvalue. And any of the non-trivial solutions that are corresponding with it are going to be corresponding eigenvectors. If that same setup, a minus lambda I times x equals 0, if this same homogeneous system has only the trivial solution, so there are no free variables, then lambda is not an eigenvalue. Now, if A is a triangular matrix, eigenvalues are really easy to find. They're just the entries on the main diagonal. But if A is not a triangular matrix, then we have to use this method we just talked about. So let's see what that ends up looking like. Oops. Okay, so let's take a look at problem 8 from section 5.1. So this is asking, is lambda equals 3 an eigenvalue of this matrix? And let's call this matrix A. So our question is lambda equals 3 an eigenvalue of A? So to find that, we first look at our special factored form of this, a minus lambda I. So in this case, because A is 3 by 3, I will also be 3 by 3. So we take 1, 2, 2, 3 minus 2, 1, 0, 1, 1, and we subtract off 3 times the identity matrix because we're checking for lambda equals 3. So it would be 3, 0, 0, 0, 3, 0, 0, 0, 3. And what do we get when we do that? 1 minus 3 is negative 2, 2 minus 0 is 2, 2 minus 0 is 2, and then 3, and then minus 2 minus 3 is minus 5, and 1 minus 0 is 1, and 0, 1, 1 minus 3 is negative 2. So here's our a minus lambda I. What do we want to do with that? What we want to do with that is we want to figure out, does this homogeneous system, so let's go ahead and augment on the 0 matrix, does this homogeneous system have free variables or not? Okay, so we're going to go ahead and row reduce this. And okay, so if we row reduce this, we end up getting 1, 0, minus 3, 0. You can check this for yourself, or you can just believe me when I say that this is what you get. So if we're looking at this, we see that there's a 0 row and it's a square matrix. So this is going to have a free variable. So that means lambda equals 3 is an eigenvalue. In order to find a corresponding eigenvector, we're going to have to see what vectors match with this. So let's go ahead and put our solution set into parametric vector form. So we have 3 unknowns, x1, x2, and x3. And we can see from the first row that x1 equals 3x3. And we see from the second row that x2 equals 2x3. And x3 is a free variable, so it just equals itself. And we can go ahead and factor out x3 and get 3, 2, 1. Okay. So again, because x3 is a free variable, then this lambda is an eigenvalue. And any non-trivial solution, so anything that's not the 0 vector, is going to be a corresponding eigenvector. So for instance, we could go ahead and let x3 equal to 1, and then we would just get 3, 2, 1, and this would be an appropriate eigenvector. Or we could let x3 equal whatever we want. So like x3 could equal 2. So 6, 4, 2 is an appropriate eigenvector. We could let x3 equal to negative 100. So negative 300, negative 200, negative 100 is one. So there are actually infinitely many eigenvectors that correspond with this eigenvalue. So you'll notice that the set of all eigenvectors corresponding to that, to a specific eigenvalue, is the null space of that a minus lambda I. So remember, we just took a minus lambda I. We just took a minus lambda I and we found its parametric vector form, and that's what we did when we tried to find a null space. So this is the null space of a minus lambda I. Well, it's not quite the null space. It's actually the null space minus the 0 vector, because the 0 vector we're not allowed to have as an eigenvector. But because the null space we already know is a subspace, we give this a special name. This is called the eigenspace of A. So the eigenspace of A corresponding to lambda is just that null space. It's the 0 vector and all of the other eigenvectors. So let's take a look at what this might look like. So if we are trying, so this is problem 9 from section 5.1. And we're trying to find a basis for each eigenspace of this matrix A. So first of all, we need to find eigenvalues. But this is a triangular matrix. As opposed to some of our other matrices we saw, this is a lower triangular matrix. But we know that triangular matrices, the eigenvalues are just the entries on the diagonal. So this matrix A, that's what we're calling A, this matrix A has 2 eigenvalues. And those eigenvalues are just those entries on the diagonal, which are 1 and 5. So it has 2 eigenvalues, so that means it'll have 2 eigenspaces. So let's start with lambda equals 1. When lambda equals 1, we have an eigenspace, or we find our eigenspace by doing a minus lambda I. So this is 5, 0, 2, 1 minus 1 times the identity, which is just the identity. So we end up getting 4, 0, 2, 0. So if we want to find the corresponding eigenspace, we're trying to look for the null space of this matrix. So we go ahead and augment with the 0 vector. And if we reduce this down, we get 1, 0, 0, 0, 0, 0. So writing this in parametric vector form, we have x1 and x2. And in this case, from the first row, we see that x1 is always going to be 0, and x2 is a free variable, so it'll just equal to itself. So this is x2 times 0, 1. And this set of infinite set of vectors, this is the eigenspace. So this is our null space of that a minus lambda I. This is called our eigenspace. If we want to find a basis for this eigenspace, then we do that just the same way we've been finding bases for null spaces all along, which is take out that 0, 1 vector. So that's our basis for our eigenspace. All right, let's try lambda equals 5. And lambda equals 5, we're going to go ahead and do the same thing. So we're looking at A minus lambda I. And we'll just take our matrix A, and we'll subtract off 5 times the identity matrix. So that's 5, 0, 0, 5. And this gives us 0, 0, 2, and 1 minus 5 is negative 4. So if we want to find the eigenspace, again, the eigenspace is the null space of this matrix. So we go ahead and take this matrix and augment it with the 0 vector. And row reduce, and when we row reduce, we end up getting 1 minus 2, 0, 0, 0, 0. So to find our eigenspace, we want to put that solution set into parametric vector form. So our x1 we see from our first row is 2x2, and then x2 is a free variable, so it just equals to itself. And we can factor out that x2 to get 2 times 1. And again, our eigenspace is the entirety of this null space. So this whole entire infinite set of vectors is going to be our eigenspace. And if we want to find the basis for this, then the basis is just exactly the same way as we always find bases for null spaces. Our basis is just this vector 2, 1. So we see that our matrix A has 2 eigenspaces, one corresponding to lambda equals 1 and one corresponding to lambda equals 5.